Hey everybody, in this video, we are going to talk about Henry's law, and this law relates the pressure of a gas to the concentration of a gas in a solution. So Henry's law states that the concentration of a gas dissolved in a liquid is proportional to the partial pressure of the gas above the liquid. Now, the equation is very simple, and because concentration is proportional to pressure, then it's going to be the equation of a line. So C of a gas, or the concentration of a gas in molarity, is equal to K, a constant, times the partial pressure of that same gas in atmospheres. Now, note that at a constant temperature, this equation can be used many times. Now, at different temperatures, K is going to be different, so don't use this equation more than once if you are doing things at different temperatures. Now, this formula proves that increasing the partial pressure of gases at a constant T, of course, will increase the solubility. This makes sense, since if you put pressure on a gas, it will be compressed and thus interact more with the solvent, since if you're more compressed, you are more likely to bump into the solvent more often, and this actually increases the solubility of the gas. So, we are going to use this equation in a problem that involves nitrogen in the human body. So, the solubility of pure nitrogen in blood at body temperature at 37 degrees Celsius, which is the body temperature, and 1 atm, is 6.2 times 10 to the negative 4 molar. So this is pure nitrogen at 1 atm, and it is dissolving at 37 degrees Celsius. Now, if a diver breathes air, and the mole fraction of nitrogen in the air is 0.78, at a depth where the total pressure is 2.5 atmospheres, so that means that the pressure of the air is 2.5 atmospheres, since that's considered everything combined, then what is the concentration of N2 in his blood? So we know that at 1 atm, which is the partial pressure of N2, and at 37 degrees Celsius, the solubility of N2 is going to be 6.2 times 10 to the negative 4 molar. Now, we got to find K from this, and we could do that using Henry's law. So, C equals K times P, and let's take a look at how that works. So we need K, first of all. So we know that the concentration is 6.2 times 10 to the negative 4 molar, and this is equal to K times the partial pressure of the nitrogen, which is 1 atm, and we get that K is equal to 6.2 times 10 to the negative 4 m per atm, so that's K. Now, number 2 states that we have to find the new pressure of N2 in the new conditions. So we have to find the partial pressure of N2 and our new conditions. So we know that the total pressure, or the pressure of the air, since that's considered everything, is going to be 2.5 atms, but the mole fraction of N2 in the air is 0.78. So we got to use a special formula that says that the total pressure times the mole fraction of a gas is going to be equal to the partial pressure of the gas. So 2.50, or wait, no, that's just 2.5 atms times 0.78, the mole fraction, is going to be equal to the partial pressure of N2 at the new conditions, which is 1.95 atms. So now we know our new conditions. We know that we have a partial pressure of 1.95 atms for N2 gas, and it's still at 37 degrees Celsius, since, remember, this is all in the body, and the body temperature is 37 degrees Celsius, and we just have to find the concentration of N2 at this new pressure of N2. So, using the formula, Cn2 is equal to K times the partial pressure of N2 in these new conditions, and we get that the concentration of N2 in the new conditions, when this diver goes down to a depth where the total pressure is 2.5 atms, we find out that the concentration of N2 in the water, or in the bloodstream, which is mainly made of water, is going to be 1.2 times 10 to the negative 3 molar. So now let's talk about why this matters. Why does Henry's law matter in the real world? We have something called the bends, which is decompression sickness, and this occurs when you decrease in depth or you swim up too quickly. And when you swim up too quickly, this decreases the pressure of the gases, of course, because as you go down in depth, as you're scuba diving down, the pressure above you, and this is caused by the water pressure above you, is going to increase, and thus the pressure is going to increase as you go down the water. And as you go down the water, it increases, so the total pressure of the gases that are inside you also increase. So conversely, when you go up, when you decrease in depth, then the pressure of the air that's inside you will also decrease. And if that decreases, according to Henry's law, the solubility of the gases, mainly N2 gas in this case, will also decrease as well. So when you're all the way down there, a lot of N2 gas is going to be dissolved in your blood. But as you swim up, the solubility of your blood drops, and because of that, the excess gas that is dissolved in your blood will escape the solution, aka your blood. And as it escapes, it forms bubbles in your bloodstream, and these bubbles of N2 gas mainly can block blood vessels and sometimes even damage them. So that's why you swim up slowly and stop occasionally during scuba diving to release the N2 gas built up in your body. So in all these cases, we are actually considering that the gas will be saturating the solution, since if a gas such as N2 can maintain a partial pressure without having to lose any partial pressure when dissolving, then this must tell us that there must be a lot of N2 gas in the air, and there's so much that it can maintain the partial pressure while losing some of the molecules of N2 to the water. And in this case, since N2 is very insoluble in water since it's nonpolar, but it does dissolve a little, then we can assume that the amount dissolved in water will be the maximum amount, since there's an excess amount of N2, and since there's an excess, that means that we tried to dissolve more N2 since we had more, but it didn't want to. So, in other words, for Henry's law, we are considering solutions that are saturated with the gas, and we are assuming that the partial pressure of the gas is constant despite losing some of itself to the water when it dissolves in it, for example. So that's all for this video. Have a nice day, everyone.